This line introduces the sample data that we'll be using to test our understanding of the multilabel binarizer . The data is a list of lists, where each inner list represents a data point and contains multiple labels. For example, A, B, indicates that the first data point has labels A and B. This is the actual multi-label data. It shows 4 data points, each with one or more labels. This is what we'll feed into the multilabel binarizer . This line shows the core function that we'll be using from the scikit-learn library. fit_transform first learns the unique labels, fitting, and then transforms the input data into a numerical representation. This simply indicates that we're interested in the result of the fit_transform operation. What will the transformed data look like? This sets up the quiz. We need to determine which statements accurately describe the output of the multilabel binarizer . This is the first multiple choice option. It proposes that the output will be a NumPy array, a specific data structure in Python, and specifies its dimensions. The second option suggests that each unique label from the input data will have its own column in the output. The third option proposes that the output will be a sparse matrix, a data structure used to efficiently store data with many zero values. Let's see if this is true. This option says the output will have a separate column for each unique label found in the input data. Think of it like creating a label inventory. If your input data has labels A, B, C, and D, the output will have 4 columns, one for each of these labels. This option says the output will have a separate column for each unique label found in the input data. Think of it like creating a label inventory. If your input data has labels A, B, C, and D, the output will have 4 columns, one for each of these labels. This one focuses on the overall shape and type of the output. It's saying the result will be a 4x4 matrix, 4 rows, 4 columns, and that matrix will be a NumPy array, a standard data structure in Python for numerical computations. The numbers 4 and 4 represent the number of samples and the number of unique labels, respectively. This one focuses on the overall shape and type of the output. It's saying the result will be a 4x4 matrix, 4 rows, 4 columns, and that matrix will be a NumPy array, a standard data structure in Python for numerical computations. The numbers 4 and 4 represent the number of samples and the number of unique labels, respectively. The input to the multilabel binarizer is a list of lists. Each inner list represents a single data point and contains the labels associated with that point. For example, A, B, means the first data point has labels A and B. This structure is common when dealing with multi-label classification problems, where each item can belong to multiple categories simultaneously. Let's explore how this translates into a binary representation. The output from the multilabelBinarizer.fit_transform method is a numerical representation of the input data. It converts the list of lists into a numerical matrix where each row corresponds to a data point, and each column represents a unique label. A 1 indicates that a label is present for a given data point, while a 0 indicates its absence. For instance, if a data point has labels A and B, the corresponding row will have 1s in the columns representing A and B, and 0s elsewhere. This transformation simplifies the data for machine learning algorithms. This is the actual output matrix produced by MultiLabelBinarizer. Let's analyze each row. Row 1, 1, 1, 0, 0, represents A, B, showing A and B are present. Row 2, 1, 0, 1, 0, represents A, C, showing A and C are present. Row 3, 0, 1, 1, 1, represents B, C, D, showing B, C, and D are present. Row 4, 1, 0, 0, 0, represents A, showing only A is present. This is a perfect example of how multi-label binarizer transforms multi-label data into a format suitable for many machine learning models. The shape 4, 4 indicates that the output is a two-dimensional array with 4 rows and 4 columns. Each row corresponds to one of the 4 input data points, and each column corresponds to one of the 4 unique labels, A, B, C, D. This structure is crucial for algorithms that expect numerical input. The columns of the output matrix represent the unique labels present in the input data. The order of these columns might not be exactly as listed, but the set of columns will include each of the unique labels. This is important because it allows you to easily identify which labels are associated with each data point. The core functionality of multi-label binarizer is its binary encoding scheme. Each cell in the output matrix contains either a 0 or a 1. A 1 indicates the presence of a particular label for a given data point, while a 0 indicates its absence. This simple yet effective encoding makes the data directly usable by machine learning algorithms that need numerical input. It's a fundamental technique in multi-label classification. This shows the initial data we're working with. A list of lists, where each inner list represents a data point with multiple labels. For instance, A, B indicates a data point having both labels, A and B. We'll use this to see how the multi-label binarizer transforms it. This is the key tool we're using from the scikit-learn library. It's designed to convert data like our input list of lists, where each data point has multiple labels, into a numerical format suitable for machine learning algorithms. It essentially creates a binary matrix to represent these labels. Before transformation, we identify all the unique labels present in the input data. This step is crucial as each unique label will get its own column in the resulting binary matrix. In this case, we have A, B, C, and D. This refers to the scikit-learn function used to transform lists of labels into a numerical representation. Think of it as a label translator. It takes a list of lists, your data, and spits out a matrix that shows which labels are present, 1, or absent, 0, for each item. This is asking what the result of using the multi-label binarizer on the provided data looks like. It's the output of the label translator, a numerical table representing the presence or absence of each label. This suggests the output is a 4x4 table matrix made up of numbers. NumPy is a Python library for working with arrays like this. It's efficient. This indicates the output table will have one column for each unique label. In the initial data, that's a column for A, 1 for B, C, and D. This explains how the numbers in the output are interpreted. A, 1 signifies the label is present, while a 0 means it's absent.